Okay, so now let's use what we know about NumPy and combine it with another package called SciPy, so Scientific Python, Scientific Computing, to actually perform some curve fitting. And what we're actually going to be doing is we're going to be assuming that our data follows some kind of sigmoid curve. So we're going to have some x data, which will be in the form of a table, and we're going to have some values y on the output that we want to try to fit a curve to, and the curve will be a sigmoid. And the equation for a sigmoid, if we just had, an input and an output, would just be 1 over 1 plus e to the negative beta times x, where x is my axis down here. And so this just takes a function f of x, and f right here now is just this value between 0 and 1, which is a sigmoid. It's a very versatile function because we can fit it to a lot of different areas. So let's see how we can actually combine this with matrix multiplication to come up with a really robust model of a curve. So let's do this. So what we want to define first is what is our x and our w data and our sigmoid. So let's formulate this problem. What I'm actually showing right here is an x array. Right? And so this array is 3 rows by 2 columns. And so let's just define x right here. It's a matrix, and it's -1, -2, 3, 1, 4, and 5. So let's pretend like these are some type of observations. There's some measured observations, and these map to some y vector. And that y vector has certain values on the input. So it might be 0, 1, 0.5, something like that. What I'm actually saying here is that, well, the first row of x, that's some feature that I want to use to predict the very first row of y. The second row of x is some feature that I want to use to predict the second row of y, and etc. With the third row, I'd like that to be able to predict the third row of y. And so the way that I can use a sigmoid to do this is actually define some parameter w. Now, w is going to be some column vector. It's w1 and w2. And I don't know what the values of w1 and w2 are, but I know that I can take w and I can multiply it by x. So in this case, I think I've actually drawn w here as a column vector, when really w in the example that I have right here, w is actually is an array here. So if we print this out, w is actually just 0.2 and 0.8 right here. So these are just values that I'm guessing. But the key intuition here is that if I take x times w transpose, that's basically like taking x multiplied by 0.2, 0.8 up here. And so I can actually use this. This multiplies by this row, and I get the value right here. So x times w transpose is equal to -1.8, 1.4, and 4.8 right here. And it's just a matter of taking this and multiplying by the first row and adding them up to get -1.8, then multiplying it by the second row and adding them up to get 1.4, and etc. with the last row to get the 4.8 value that I have right here. So by taking just a two-dimensional w vector, multiplying it by x, I can now convert. So x times w transpose is just a vector of values. And so those are the values that we're actually going to pass through a sigmoid and say, oh, okay, well, let's now actually pass those through this f of x function, which is 1 over 1 plus e to the -x right here. So I'm able to take these functions and they map now between 0 and 1, right? So after I've passed them through the sigmoid function, f of x is going to have somewhere between the values of 0 and 1. So if my y values are all between 0 and 1, and that means that I can take this vector, pass them through f of x, and now f of x becomes my prediction for y. So we'll call it y hat is now equal to f of x, and x was, sorry, I'm abusing my notation here. So instead of calling this x, let's call it something like alpha right here. So f of this would be x of x times w transpose to get y hat. And so my y hat vector is something that I could define a little differently. So let's actually do that right now. So if we defined y hat to be the sigmoid of this, y hat is just going to be equal to 1 over 1 plus, and then I'll use np.exp, which is an exponential, and then I'm just going to take the negative dot product of x and y. So this becomes, if this were w x times w transpose, this would be 1 over 1 plus e to the negative x times w transpose right here. And so that's exactly what the function is that I'm representing. This is f of x w transpose. Right? That is going to be equal to my y hat, my prediction of what it is. So that's what this explicitly defines the function that I have. So if I actually call the function y hat, what I can see is that now I've converted x, which was 3 rows by 2 columns, to just be 3 numeric values, and maybe those are the values that I want to be able to predict my y values from, right? So what I'm really going to want here is I want a w that when I multiply it by x and stick it through the sigmoid function, what's the best w such that the difference between y and y hat is extremely small. And the way that we can actually define that is say, oh, okay, well, for each row of y and y hat, let's say we have y right here, it's a column vector, and we have y hat right here, it's also a column vector of some type of predictions. Well, I can say, well, what's the difference between this and this value, the second value in my second prediction, the third prediction, or sorry, the third value in my third prediction? I can just take y minus y hat right here, and that gives me another vector, right, which is the difference between them. I can just square that and sum the whole thing up. And what that basically tells me is it's the sum squared error between what I want and what I've predicted, right? And this is typically known as an objective function. It's the objective that I want that to be as small as possible. So my objective, it's a function of w, because remember y hat is also a function of w. And it's just equal to the sum over I of y minus y hat, all quantity squared. Right? Now these are two vectors, and what I really want to be doing here is summing over each row. So we need some notation for each row of x and each row of y. And so the way that we'll do that is I'm going to say I have this cap x matrix, but I'm going to say that I can break that down into rows. So x of 1, I'll use a superscript with parentheses around it. That's the entire first row. X of 2, that's the entire second row, all the way down to however many examples I have, say x of cap n. That's the whole row. And what that means for y is that y is a column vector, and these are just numbers now. y1 is just a single number that I want to predict. y2 is a single number all the way down. There are n number of rows right here. And y hat, similarly, can be drawn out. And so now really what this objective function is that I've drawn here is the sum over I for the ith example of y hat and y. And I'm going to take each of those differences, square them, and add them all up, right? And so what I want to do is minimize this objective function. So let's define my objective function now here in Python. So if I define my objective function, well, I need to know what w is, I need to know what x is, and I need to know what y is. And the reason for that is because, based on w and x, I'm going to say, oh, okay, let's call the function y hat of x and w. It's a function of x and a function of w. And then I will say y minus y hat right there, which returns a new vector. And now NumPy has this really nice operation where after I've created that vector, I'm going to square it. Right? So I take this whole parentheses and I square each of the values, so it does an element-wise squaring, and I'm just going to call np.sum, so I will take the sum of that. So what I've defined now is exactly my objective function, and as I change the values of w, I will change what the value of this objective function is, and we'd like that value of the objective function to be as small as possible. So let me define this. And now let's actually define some example data that we have right here. So if we want this to be something that is solvable, what I'm going to do is create a random matrix, and I'm going to call np.random.rand and basically tell it that I want a matrix which is 100 rows by 2 columns, which means I have 100 observations, right? My cap n right here is equal to 100 observations. And now I'm also going to be telling it that I want to have 2 different columns of x. And that means a couple of different things. That means x right here is going to have the, so if I were to draw out, create a new thing, so x1 right here, it would have the x1 of 1 and x1 of 2. It's just a two-dimensional matrix, right? So a two-dimensional vector right here, where the subscript right here is how I'm indexing into each of the elements of the row. So these denote the column that I'm at right here. And that means that w, it's going to be w1, w2. I just need to have 2 different values that are part of w. So we get some random values back here to populate x random. And then I'm going to define, okay, here's some w that I know. And the values of w that I'm trying to find are going to be 5 and 3. So I'm going to create this variable y, and all I'm going to do is I'm going to pass my random data xrand, multiply it by w exact, and then take the logistic function, or the sigmoid function, of those values and set that equal to y. And then I'm going to add a little bit of random noise on top of y that I have right here. Okay, so I add some random noise on top of y. So y is the vector, it's exact, it's x multiplied by w passed through a sigmoid. And then I just randomly add some noise to it. So now y is not an exact value of y hat x rand and w. So let's actually look. So let's say my w temp, so I don't know that w is actually 5 and 3. Let's say I were to guess that it's actually 5.5 and 3.2. And then I pass my w temp, my x random, and my y values that are my raw y values, and I pass those through, and I get my sum squared error. Well, when w is 5.5 and 3.2, I get a sum squared error, which is 0.337, right? 0.3369. And so essentially it means that, yeah, I'm not too far away. But if I choose w values that are even closer, so 5.1 and 3.1, then I can get a sum squared error of 0.3166, so even smaller, right? And if I put my objective function when I use the exact value of w, I actually get 0.3199. So that's actually slightly bigger than when I had 5.1 and 3.1. And the reason is because I've added this random noise. So the w exact values, even though that's what was used to create the function y, once I added the random noise, I slightly changed what the objective function is. So the w values are going to be close to 5 and 3, and I'd like to predict those as close as possible. So as a little bonus right here, let's actually graph out the values as I change what the w values are. So what I'm going to do here is I'm going to import a package called matplotlib, and I'm going to import the plotting function of that. And I'm going to tell my notebook that I'm going to be plotting things, and don't try to plot them in a new figure or make an interactive figure in Python. Just actually stick them in the Jupyter notebook. And so we will actually use this extensively a lot in data science. But for right now, all I need to do is I give it the x values that I want it to calculate, so the horizontal axis values and the vertical axis values. And so what I'm going to do here is I'm going to graph the dot product of my x times w exact, and then I'm going to graph that So I'm going to graph y versus the dot product of my exact values of w and x. And then I'm going to define this w temp variable, which is 5.5 and 0.2, so not the w exact that I have. And I'm going to do the exact same thing. I'm going to take the dot product between them, and then see, well, how do those actually plot when I plot them versus y? So let's plot this out, and just a moment to load. What we're actually seeing here is when w is close to the actual values, this starts to look a lot like a sigmoid function, right? So the sum squared error when I pass this through a sigmoid and take it to y is going to be small. However, when these w values are not close to the actual values, I get something more random. So it's going to increase my mean squared error, right? And so just using this objective function and trying a bunch of different w's, I could actually figure out maybe something that's close to the values. And so SciPy has a built-in function called minimize. And what that does is it says, okay, if you give me an objective function, I will take the values of some w and I will adjust them until I'm able to minimize, as much as possible. I might get stuck somewhere, but I'll try to minimize as much as possible to get that objective function to be as small as possible. And so the only thing we need to do is say, okay, well, we'll give it a random starting value of w. We don't know what w is. We actually know from our example that we know the exact values are 5 and 3. But what we'll do is we'll give it a random starting point, and we will give it additional arguments x random and y, so that we can calculate our objective function. And then all I'm going to do is give it that function obj, the objective function that we calculated, and tell it to minimize it. And what it will do is return to me the found values of w. So if I let this run, it runs very, very quickly. And I can see that the optimization process terminated successfully. It evaluated my objective function 136 times. And it was able to find that the predicted values are 5.1 and 3.1, which are extremely close to 5 and 3. So this is great for when we don't know anything about the mapping between, let's say, the values of x and the values of w. But it turns out we can make this optimization a lot more efficient by taking the derivative of the objective function, which is what we'll do next.